But recall we actually want to solve this in general, so that means we want to find a closed formula for h sub n involving the index n, and so we do this using the iteration method that we talked about before. So you could do that like we did before by starting with h1 and building up to h sub n, but since we had so much trouble going the other way, starting from hn and going down and finding the pattern, we're going to try that again to see if we can make that method a little bit more clear for you, just in case you need to use it at some time in the future. So we are going to use an iterative approach to solve this recurrence relation by repeatedly expressing h sub n in terms of the previous terms of the sequence. So we're going to start from the top and work our way down. So we're going to start with the original recurrence relation we established. So h sub n is equal to 2 times hn minus 1 plus 1. So we went through the process of solving this puzzle to get this recurrence relation, and now we want to repeat this equation a number of times until we can develop a pattern. Okay, so in this case, we're going to substitute in the same recurrence relation except for h sub n minus 1. So recall that we substitute a value for hn minus 1 into this equation. So it's 2 times h sub n minus 1, which, if we follow the same pattern of our recurrence relation, is 2 times hn minus 2. So the previous term from n minus 1 is n minus 2. So there are 2 times we move the n minus 2 many disks from one peg to another, and then we move the largest disk, so the n minus first disk in this case, and that gives us that relationship, and then plus 1 for that moving that nth disk. So rewriting this a little bit to start to develop our pattern, know that we can simply multiply this 2 through here, so 2 squared times hn minus 2 plus 2 plus 1. And then we're going to repeat this, substituting in a value for h sub n minus 2. So recall that this is simply 2 times hn minus 3, so the previous term of the sequence, plus 1, and plus 2 plus 1 here, and then we multiply 2 squared through here, so we give 2 cubed times hn minus 3 plus 2 squared plus 2 plus 1. So I think it's easier in this particular example to see where we are going. So repeating this process, we want to figure out how we substitute in h sub 1. So we need to develop a relationship between this exponent here and our index here to determine what happens when we get to 1. So how is 3 related to n minus 3? So just like before, notice that 3 is actually equal to n minus 3, right? If we take n and subtract n minus 3, n minus n cancel out, and subtracting minus 3 gives us 3. So that tells us that this exponent is n minus the index here. So if we're looking at replacing h sub n minus 3 with h sub 1, this is the index. So with that relationship in mind, this exponent is simply n minus the index here. Recall, because 3 was n minus 3. So the index, or the exponent here, is n minus 1, n minus the index of the sequence we're looking at. And you can compare this exponent here with this index to notice that it follows the same pattern, right? So 2 is equal to n minus 2. So this exponent can be written as n minus the index. And so that's where we get n minus 1 on the exponent here, because that's n minus this index. Okay, and then notice that beyond that relationship, we simply add decreasing powers of 2. So from n minus 1, we would have n minus 2, then n minus 3, all the way down to 1. And then recall that our initial condition for this recurrence relation was h1 equal to 1. We simply moved one disk from peg 1 to peg 2. So substituting h1 equal to 1 into this equation, we simply get a decreasing sequence of powers of 2 from n minus 1 down to 1. So we have developed a closed formula for h sub n as simply the sum of powers of 2 from n minus 1 down to a power of 0. Recall, 2 to the power of 0 is 1. And so now we can use a formula for the sum of the terms of a geometric series. So notice a geometric series is one in which we have decreasing or increasing powers of a particular value. And so you can review sums of the formula for the sum of a geometric series and get that h sub n can actually be written as 2 to the power of n minus 1. So this tells us exactly how many moves it takes to solve the Tower of Hanoi puzzle with n disks. So it takes 2 to the power of n minus 1 many moves to solve the Tower of Hanoi puzzle consisting of n disks. Okay, so next we're going to look at counting the number of bit strings of a particular type.